Welcome everybody to the fourth lecture of our machine learning class. Today I'm going to talk about model validation. So let's review one more time our general setting. We have inputs X, our model F, which produces predictions Y hat, and we train F to be as close as possible to the labels Y. But we haven't yet talked about where these X and Y's are coming from. We usually think of the world as some space, and the space really is relating to the features, right? So whatever attributes we have in X, that really defines what our space looks like. And within this space, we have so-called data domains from which we sample. So let's think of a simple classification task of images. One of these origin data domains may be dogs, so here in blue, and yellow could be cats. And so what we do is really we sample from these underlying real spaces our images. Yeah? Now, because we're sampling, the next time we do it, we won't get the exact same X's and Y's again. They will look a little different. So, for example, here in the left is our first sample of X and Y's, and the next time we do it, we will see some slight changes. For example, first time we did it, the model that we could train or had trained did not see any of these parts of the actual data domain. Yeah? The same here in this region, we didn't have any knowledge that this part actually belongs to cats. In the second sample, we do have some data points down here, and we do have some data points up in this actually previously blue region. And our model that we trained may come up with a decision boundary that I've drawn in here and may perform really well. But on the new and unseen data set, exactly in this region here, it may make some mistakes. Yeah? And that's exactly what we are going to look at. We want the model trained on set 1 to extract those relevant features, those structural properties that are relevant to predict whether it's a dog or a cat. And we're going to test this not on the training data itself, but on new and unseen data. So today we're going to talk about how we can quantify the model's performance. Yeah, we will look at the errors that a model can produce and try to assign it to different sources, different components that we will identify. We'll also look at different metrics that we can use to quantify different aspects of the model's performance. So for a regression task, we can build a model which here would be this blue line on the training data, on the blue data. And we can compute the loss, which is minimized in training, and we call this oftentimes in-sample error because it quantifies the error of the model on the samples that we have seen. Now, if we test or quantify how well the fit is of the blue line to the new data, we call this out-of-sample error. And that is exactly the error that is the most important one, yeah, because this is closer to what the model in production would see, because this will see new data, and
should generalize to this one too. So that's why we call it generalization error. And you will see shortly why this oftentimes is also called test or validation loss. Now you may ask yourself, how are we going to get all these different data sets? Well, you don't. You just take the data set that you have and then you split it up into one portion that you use in training and another portion that you only use for validation purposes. Yeah, so in the following, we'll use this Z as a set of X and Y's, so inputs and outputs, and we'll take Z and split it up, take the training set to train the model F, and then we validate F using Z val. So how do we implement this split? Well, first of all, we decide for a fixed ratio. So for example, 10% or 20% are going to be our validation portion. Yeah. So we take our data, we randomize the order, and then we take a fixed window, maybe at the end, maybe at the beginning, and then we take this data as our validation set. The problem now could be that the sample that we draw from the original data set, leaving out a couple of data points, 10%, 20%, that exactly these data points that we leave out were really relevant. Yeah? And so whatever we fit, whether it's a line or something more complex, may not fully represent the entire data. Yeah. So for example, here in this line fit, we had the blue data in our training set, but the fit is something different than we would have obtained if we had all the data. And so what we therefore could do is we repeat this split a couple of times with different portions of the data set as validation set and training set. And then we train our models on the train set, and then we see how it performs. But to get an idea of how a model would perform on unseen data, we compute the average loss over all different models and all different validation sets. So doing this, the train validation split over and over again is called cross-validation. And it works like that. So we take our data, we shuffle the data, and then we take a window that has our width that we predefined earlier, and then we sample non-overlapping subsets within our data that we then assign to our validation set, and the rest is training. Yeah, and so we can do that so many times depending on what your split size is. Yeah. So for each of these splits, you train a model on the training set, and you test this model on the validation set. You get a loss value, and you can collect many of these loss values for all the individual models, and then look at the distribution. So how many times you have obtained a loss of a certain value. So many times something around 80, not so often times something around 70 or around 100. And the interesting properties now here that you can read from this distribution are the bias and the variance. Bias is really the average loss, so averaging over all individual losses gives you the mean of this distribution. Yeah, and this is important or relevant because this gives you your expected loss on unseen data. Yeah, so if you wouldn't know, and you usually don't know what your real world data will look like in production, you can estimate a loss with the bias. Yeah, so this is what your model will perform. This is the expectation, yeah, on average. Now, how confident you are with this prediction is this variance, right? So the broader this distribution is, the more variable the model could perform on new data. Yeah? And so your prediction is less likely to be exactly whatever, so 80 or so, yeah. If the spread is large and if it's very tight, you are very confident that your model will be like that. So you want the bias and your variance to be as small as possible. So that means the average loss that you make with your model should be close to zero, obviously. And also the variance should be very, very small. So you're confident that the bias that you expect is the actual bias that you expect is close to the one that you've estimated before in this distribution. Now, how can we reduce the bias and the variance? Well, look at the regression task again. We had sampled our blue points here, and the blue line fit here gives us an okay kind of loss. But what we could do is we could just, make the model more powerful. So in a way, give it more flexibility to adapt to the training data. And then, this could lead to us taking line segments that connect all the training data. And now, well, this gives us a very, very good MSE, so mean squared error loss, which is 0 here. But that is only on the training data. So that's not really good. Yeah? So because if we take new data, this will probably perform terribly. Yeah? And that was what I meant with it should capture. So the model should capture the most relevant structural properties. And here, because the data was generated using a line or a linear model, the model is really, so the line model, the blue line here is really the best that we can think of. And making the model more powerful won't give us anything. It just will produce a higher generalization error. Yeah. So look at the distances of all these yellow or orange points to the red line segments. This will be bad. Yeah. So this will be bad, and we don't want this kind of model. But what about more complex data? Yeah.
So let's say we have data sampled that looks like this. So where's my pointer here? This looks a little bit like a U turned upside down. Now, it doesn't look like a line. There's some more in it, and our line fit, whatever data it would have seen. So either from the blue first sample or now here the second orange sample, it will never perform well because it failed to capture the relevant structural properties. So while a line model simply can only underfit the data, what about piecewise linear models? So I have trained this blue function here on blue data, and now you see that yes, it kind of captures this U shape, but it also has a lot of quite large errors that stem from the fact that it overfitted on the blue data.
So what we are looking for in machine learning is to find a balance between models that have enough power or flexibility to to grasp even those tiny structural properties that are still relevant for a good prediction, but they are not powerful enough to overfit to the data. So to summarize, we have our loss, which as we increase the model's complexity, and that's speaking in generally, sometimes more complex models don't get better, but so as we increase the model complexity, the bias will probably go down, yeah. But what we see isn't that we reach a loss of zero, because as the model becomes more powerful and um, gains the ability to overfit to the training data, the loss will go up again. Yeah, and so that's the second part that we discussed, the variance. So the inability to generalize to structures that make up the problem then turn out to be increasing the loss, and so we want to be here at this sweet spot. Yeah? So let's have a look at how our error, our loss, for the validation and for the training phase will look like if we increase the number of data points in our data sets. So in the limit, let's say we have unlimited data that describes the problem perfectly, but usually we don't have unlimited data. And let's have a look at how we start. So think of just 2 points, and we wanna fit a line through these points. Obviously, in training, this is possible with every, even the simplest model. So the training error will be zero, but then validating this will produce a lot of errors, right? And that's because, well, even simple models can overfit on tiny amounts of data. Yeah, but as we increase the data points, the number of data points, the model in training can see much more of the underlying problem, and then reaches, in the limit, its capacity. And even if we use a very powerful model in training, it may not be able to reduce this training error to zero, because there is still some unreducible irreducible error. So think, for example, of this region in the cat and dog example, where both yellow and blue dots originated from. So these are not, I don't know, hybrid species. Um, so we either have a dog or a cat, but in the feature space that we used, it's impossible to separate these two kinds of cats and dogs. Yeah? So this kind of error will always be there. But increasing the number of data points now, and especially in the limit, now gives the model everything it needs to learn. And let's say we have a very powerful model. Let's say overfitting to everything is allowed. Yeah. Okay. But since we don't have unlimited data, we have to find a way to cope with bias and variance and trade these two against each other. We do that often by tuning hyperparameters. So values that you choose before you even start training the model. And those values, for example, may correspond to the number of nearest neighbors or so, yeah, in your classifier, or the number of clusters that you try to find using k-means. And so the choice of hyperparameters really, can make a model very different. Yeah? Could make the model more powerful, less powerful, and all those things. And the question is, how do you optimize this? And so think of doing your cross-validation and testing, optimizing not just your parameters, but also your hyperparameters on your test or validation set. and then you give your model, your best model, out to your customer, and in production it produces much higher errors. So what happened is that you overfitted again with the hyperparameter optimization on your validation set. So what you would usually do is you hold back your test set. That's another portion of your original data set, that you never use in any of these optimizations, neither in the optimization of the parameters nor in the optimization of the hyperparameters. And you just use it to test or to quantify the performance of your model. Yeah? So you can tell your customer the model will perform like that. So this was Bias-variance trade-off, generalization, and how can we quantify the performance of our model on data, so we have like an expectation of what the model will perform on unseen data in the real world. Now, the loss that we have been using here is a very important objective, and it's obviously also a relevant metric, and that's why we're using it in the training. But besides the loss, there can be many other metrics that are also quantifying relevant aspects of what your model is doing. Sometimes these metrics are undifferentiable, and that's why they're not so amenable to optimization, but they're still relevant, and they can still be used to get a picture of what your model is doing and in what ways it may fail. Yeah, because we want to know exactly what's going on. So the mean squared error is something that is, for regression, a decent metric. Yeah? So we can fit a line, and then we can compare two line fits, and then the better fit has a lower MSE. But what if we wanted to compare different models, different shapes of or curves that we want to fit? We oftentimes in this case apply the so-called coefficient of determination, or R squared. And R squared is really just comparing the mean squared error of our model to a baseline model. And in linear regression, the simplest baseline that we can think of is just the average of the data. So visually, what we do is we take the difference of the label to the prediction, and in the baseline model, the prediction would just be the average of all labels, of all y's, and square this, and then we take the mean of all of these squares. So the mean of these squares here is much larger than the mean of these squares, and R squared is 1 minus, well, something small over something big, so that should be close to 1. So that's a good model. We explain, the model explains most of the variance. Yeah. And so what about a model that is really not explaining variance, but is really worse than the baseline? Then this number here in the top will be larger than the number down here, and R squared is negative. Yeah? So that's usually meaning we shouldn't use that kind of model. Yeah? So R squared compares the performance to the simplest model possible. We don't have to use the average. We can compare this to other models that we want, but in linear regression we usually use the average. and usually is between 0 and 1, but sometimes, if we have a really bad model, it can become negative. Let's have a look at binary classification, just like we looked at in the previous lecture with logistic regression. Our classifier receives inputs x and returns an output that is between 0 and 1, which could be interpreted as the probability of the input x to belong to class 1. Now, we usually apply a threshold, so the prediction isn't in the range of 0 between 0 and 1, but rather 1 or 0. Yeah, and so looking at this model and the data, there's 4 things that we want to look at. One is which are the actual positives, right? So these are all data points that have the label 1. Which are the actual negatives? So those data points with label 0. And since we do have a classifier, it returns numbers above, it returns a 1 for values whose probability is above 0.5, so the threshold. Yeah. So this would be in this region, and the prediction of data points belonging to class 0 are here. Yeah. So all x's below this marked 1 here will receive a prediction of 0. And to review exactly what's happening with all the data in this binary classification task, we look at how many actual positives are predicted as being positive and how many are predicted negative. And for the other class of points as well, so all those that are labeled 0, so the actual negatives, how many do we sort into the positive category and how many are predicted correctly as a negative? And for this class here, so the positives that have been predicted positive, those we use the term true positives, or TP in short. So those are the ones that live up here. They are in the right half space, and then we have negatives that have falsely been predicted as positives. Yeah? So those are the errors that live down here, right? So these are actually labeled 0, but since they are above the threshold, we label or we predict them to be a 1. So these are the false positives. True negatives now are called those that our algorithm correctly classified as negatives. And again, these are these points below here. And then we have false negatives. So data points that incorrectly have been labeled or predicted to be negatives, but they are actually positives. So these are those data points up here. So for a given data set, this matrix here can be just populated, just calculated from comparing the outputs of your model with the actual labels. And so you generally want your model to have high numbers in the diagonal and values close to 0 on these false positives and false negatives. Yeah. Now, we usually use this matrix as the origin of for the computation of different other metrics. And I'm going to show you a couple of things that we would like you to learn. So the most common metric is really to look for how many of these points were correctly classified. Yeah, so they fall either in the true positives or the true negatives category. So the accuracy is the number of correct predictions, so the sum of these two, TP plus TN, divided by the number of all predictions. Yeah? So the number of data points. Yeah, and for the example of the previous slide, we obtain an accuracy of 83 or 84%. So accuracy is nice, and you will see that many times, but sometimes some predictions are more important than others, and your metric should reflect that. So for example, if you have a model that predicts catastrophes, so if, I don't know, earthquakes are going to happen in the next hour. So we cannot afford to miss this prediction, right? So to have earthquakes that we do not predict. Yeah? And so, I mean, what we could do is we could take our threshold, so 0.5 or whatever, and the corresponding axis here, and move this threshold so much down that all the data points are within the output one. Yeah? Now, before we talk about the errors that we make because we shifted this threshold, let's look at a metric that's called sensitivity. So that looks specifically at the positives. So how many true positives did we predict relative to the amount of positives that there are? Yeah. So 100% means the algorithm is very sensitive, right? So it triggers earthquake warning as soon as there's evidence, and it always triggers when there was or there is an earthquake. Yeah. Now, you can correctly say, what if I just move the threshold, all the way down, so every data point is classified as one, as an earthquake, or as, I don't know, a medical test condition that is, that would be really critical not to detect. Yeah? So a COVID test, for example. And yeah, you're right. Very sensitive tests always come with the risk of falsely classifying negative samples as positive. Yeah. And so in our earthquake example, false positives may be expensive because the evacuation procedures and whatnot that would follow. And that's why you always look for another part that we'll focus on now. So, but sensitivity means we care about all the positives. We try to decrease the amount of false negatives. Yeah. So we want all of the earthquakes to be detected, all of the COVID infections to be found, even under the cost of falsely detecting patients that have no COVID as COVID infections. So, on the other hand, if you consider the false positives now to be very costly, yeah, you, for example, your countermeasures, against a nuclear strike, are like 1,000 rockets that would destroy whole continents. Yeah? You don't want to do this, except it's really, really necessary. So your model should be very specific, and you don't want, you know, false positives to trigger Armageddon. Yeah? And so similarly to what we did earlier with sensitivity, we can introduce specificity, which is just the rate we have classified true negatives relative to all the negatives here. Yeah. And we can reverse this view. So if we want to know what the amount of false positives really was in the set of all negatives, we define something that's called fallout, and also the amount of false negatives. So the samples that we missed to classify as positives is called false negative rate, and is defined as the number of false negatives over all positives. And now what you will oftentimes see is something that we call receiver operator characteristic, or ROC curve. That's a curve that lives in the space of the false positive rate here on the x-axis, and the true positive rate on the y-axis. So imagine you have your classifier, and it's using a threshold like we just saw on the previous slide, and then you can tune your threshold and obtain different values for the sensitivity and the false positive rate. Yeah, and then you use these measurements, and then you obtain this kind of curve. And now the idea is that, well, first of all, you can describe the behavior of a model in this curve, right? But you can also define your optimal threshold given this curve. Yeah. So, for example, the optimal value would probably be here somewhere. So we have a high sensitivity, but also a low false positive rate. So in contrast to asking how many of my earthquakes were reported or predicted earthquakes, we could turn this question around and ask, okay, how many of my predicted earthquakes were actually earthquakes? Yeah? And this is called precision, or sometimes positive precision, or positive predicted value, where now in the denominator we will always look at our predictions. So this is our total number of positive outputs, positive predictions. And similarly, we can look at the negative precision. So that's the number of negatives, of true negatives that we predicted to be negative, or within the set of negative outputs. Let's compare these four metrics: sensitivity, specificity, positive and negative precision. We have the space of all our data divided into positive and negative outputs. Yeah? So these are the real labels, positive and negative. And the output of our model that is 1, so that corresponds to label P, positive, is within this box. Yeah? Everything outside the box is what the model would classify as negatives. Now, in sensitivity, we compare the true positives, so all the data that has been classified as positive, to all within P. Yeah? So a good and very sensitive algorithm would try to cover most of P, disregarding the cost that comes with covering something within N. Yeah? We just look at the positives. And the opposite is true for specificity. So we only regard all the negatives. Yeah? So a very specific model, very specific predictor, would try to move this box into P, not covering anything within N. Yeah, so all the predictions, all the positive predictions, would fall into the positive area. Even though some of it around it may still be false negatives, but if it says so, it will be a positive. Yeah. And there's so a very specific model has a low chance of misclassifying a positive. Yeah? In the remaining two metrics now, we look from the perspective of the model. So we look at the data that is predicted positive, so either true or predicted false positives. And then we look at this proportion. So a very precise algorithm would have almost no false positives. Yeah? And so, this box could move into P again. Therefore, decreasing the size of the false positives. Yeah? Although, it could be a very small region that we cover. So we would be very precise, and by the way, also very specific, but not very sensitive. Yeah? And the negative precision now is again a little the contrast to this. So we only look at the negative predictions, so the true negative predictions and the false negative predictions. So if our model would try to optimize negative precision, it would need to cover again most of P with its predictions. So there's no false negatives. Yeah? And for the sake of completeness, there are two more missing metrics. One is called false discovery rate. Again, we only look at the positive predictions and quantify the number of false positives over the sum of all positive predictions. Yeah. And again, we also have something that looks only at the negative predictions and quantifies how many of false negatives we have relative to all the negative predictions. Yeah? I hope you're not too confused right now. And by the way, this matrix here is called confusion matrix. It reflects how much the algorithm or the model is confused. Yeah? And all the metrics that we've just introduced reflect certain aspects of the model's confusion. Yeah? But since we do not want to throw around with 8 different types of metrics here, we need oftentimes a value that kind of combines everything. And one of the things is very popular. It's called the F1 score, and it's defined as the harmonic mean of sensitivity and precision. Let's have a look at 3 extreme cases. So I hope you agree with me that this is a very, very good case. So all the positives were predicted positive and all the negatives were predicted negative. So this is good. Yeah? In another case, we have an algorithm that predicts 10 of these positive samples as correctly being positive, but also the other 10 as negatives. Yeah? And also we could have an algorithm that again predicts 10 samples to be correctly being a positive sample, but also 10 of the negatives were incorrectly classified as positives. So for the first case, we have a true positive rate of 1 and precision of 1 as well. Yeah, so all of the predictions of the positive predictions were actually from P, and all samples from P were predicted positive. Yeah? So that's a perfect case, harmonic mean of 1. Then for the other case, where half of the positive samples were wrongly predicted negative, we have a true positive rate of only 50%. Because only half of them were correctly classified as positives. But the precision, so looking at all the positive outputs, is 1. So all of the positive outputs were actually from P. So our F1 score is 2/3. And the same score results from a classifier that does this. So we now have predictions, positive predictions, that 50% come from P and the other 50% comes from N. Anyway, if we only look for the positive samples, all of them were predicted as positive, so our sensitivity is 1, although our precision isn't good. Yeah? So we look at how many of the true positives were among all the positive predictions, and that was just 50%. And again, we come up with an F1 score of 2/3. So we haven't yet talked about multi-class classification metrics, but really these are very similar to what we've just heard. So let's play with one of these examples with 3 classes, C1 through C3. And let's say we have our confusion matrix, which of course now needs to be 3 by 3 with the predictions for these different classes. Now, obviously, the first thing that we could do is to see, okay, how many correct predictions did we gather? So 3 correct predictions for class 1, 5 correct predictions for class 2, and 4 predictions that were correct for class 3. Now, these, of course, need to be summed up and compared to the total number of class-specific samples. Yeah? So, for example, 3 plus 5 plus 4 then needs to be divided by the number that we've just given you here. So 5 for class 1, 20 for class 2, and 13 samples for class 3. So the overall accuracy of this model would be 32%. And all the other metrics really can be applied to multi-class classification as well. Now, since we don't have 2 classes, we only have let's say 1 positive class and the rest of the world, let's say. Sensitivity, for example, and all the other metrics would apply for only 1 class, right? So we could calculate sensitivity for class 1 and a sensitivity for class 2 and so on. And let's do this for class 1 real quick. So we look at the true positives, so these are 3, and divide this by the number of the number of samples within class 1. So we said 5, so the sensitivity of our algorithm here is 3/5, so 60%. And let's have a look at specificity. So again, we will do this per class. Yeah? So we can calculate a specificity for class 1, but now we look at the outputs that correspond to all the other classes. So the rest of the world, let's say, yeah. And we look at the output of the classifier that corresponds to the other classes. Sum all these up. So this is 18 divided by the total number of samples in all the other classes. So 33, and then we have a specificity of the classifier of almost 58%. So that was it for today. I hope you enjoyed Bias variance and also the validation metrics. I hope you will now be able to implement these and apply these things to your current assignment. Yeah, that was it. I hope you enjoyed it. See you all next time. Bye.